Imagine an electron traveling through a void. There are no obstacles in its way and no magnetic fields pulling at it. Yet, as it moves, the electron shifts its course, reacting to an influence that isn't supposed to be there. For centuries, physics followed a clear logic. To move an object, you have to touch it, or it has to pass through a local field, like the magnetic pull surrounding a magnet or the gravitational tug of a planet. In this classical view, these fields are the primary reality. If you measure the strength of a field at a specific point, you know exactly how it will affect any particle passing through that exact spot. According to these laws, a region of space with zero fields should result in zero physical influence. But we have discovered that the universe does not always obey that limit. This discrepancy traces back to a calculation problem from the 1800s. Early physicists found it nearly impossible to track the complex three-dimensional vector forces acting on a single point when multiple planets or charges were involved. To simplify the math, researchers like Sir William Thompson developed a shortcut known as potentials. This method replaces a chaotic mess of directional arrows with a simple map of numerical values. It is like turning a storm of wind vectors into a calm altitude map, making the behavior of a system much easier to predict on paper. For decades, the physics community treated these potentials as a pure accounting trick. They were considered a mathematical convenience with no physical existence of their own. For an entire century, science assumed that these equations were merely a description of the math, not the source of the physics. In 1959, David Bohm and Yakir Aharonov challenged that assumption. They realized that the equations of quantum mechanics, the laws governing the microscopic world, required these abstract potentials to function, even in places where the fields themselves were absent. They proposed a setup using a solenoid, a tightly coiled wire that traps a magnetic field inside its core. If the coil is perfectly shielded, the magnetic field outside is zero, creating a void where an electron should feel no force. Bohm and Aharonov predicted that an electron wave passing through this field-free void would still be altered. The particle's wave function would stretch or compress because it was sensing the potential, despite the lack of a magnetic field. The idea faced immediate resistance. Many physicists, including Niels Bohr, rejected the claim that a particle could be influenced by anything other than a local physical force. Skeptics spent 30 years arguing that early experiments were flawed. They claimed the results were caused by magnetic fields leaking out of the ends of the cylinders, rather than the potentials themselves. To prove the effect, someone had to create a magnet with no ends, a geometry that left no possibility for a field to leak into the path of the electron. In 1986, Akira Tonomura at Hitachi addressed the leakage problem by adopting a geometry with no ends, a microscopic torus, or donut shape. In this torus, the magnetic field is trapped in a continuous loop inside the donut's walls. Because the shape is a closed circle, the field cannot escape. This creates an absolute zero-field environment in the center hole and the surrounding space. Tonomura fired a split electron beam toward the magnet. One half traveled through the empty hole in the center, while the other half moved around the outside. Neither beam ever touched the region containing the magnetic field. When the two streams recombined, their interference pattern had shifted by exactly half a phase. Even though the electrons never encountered a magnetic field, their behavior changed because of the potential surrounding the donut. Tonomura's precision experiment provided the evidence needed to confirm that potentials are a physical reality, effectively ending the 30-year debate. This discovery indicates that the magnetic and electric fields we measure at a single point are actually side effects of a deeper, underlying geometry. It shifted the focus of physics toward topology, the study of how the global shape and connectivity of a space dictates the behavior of the particles within it. In a space with a hole, like the center of the torus, the path of a particle is informed by the connectivity of the entire system. The potential allows the particle to sense the magnetic field trapped inside the donut without ever actually touching it. Particles do not simply react to what they encounter locally. They are influenced by the global topological structure of the universe. This topological perspective is now leading physicists to search for a gravitational version of the Aharonov-Bohm effect. Observing this effect with gravity would help bridge the gap between our description of the macroscopic universe and the laws governing the smallest scales of matter. It suggests that the abstract mathematical rules we once used for convenience are in fact the literal fabric of nature. We are uncovering a universe that is invisibly interconnected, where a particle's motion is dictated by the very shape of the space it inhabits.